Hello, everyone, and thank you for joining us for today's webinar with Clean Energy Associates, where we are going to be taking a deep dive into battery energy storage system, or BESS, manufacturing. I'm Andy Colthorpe, editor of Energy-Storage.news and deputy editor-in-chief at Solar Media, which also publishes titles including PV Tech, the world's first and best solar technology site. We are really excited to be hosting CEA's expert speakers in this session, who will be able to give us some of their many insights from more than 30 gigawatt hours of inspections at BESS production lines all over the world. Now, you'll hear a bit more of an introduction to CEA itself and its work in the sector from our speakers shortly, but needless to say, we are in good hands here, folks, and I can promise that even the most experienced among you will find plenty of things to think about. Meanwhile, those that are newer to the sector, or perhaps less technically minded, will also benefit and learn a lot from watching and listening. Now, figures vary, but analysts that cover the energy storage market are in broad consensus that 2024 will mark a surge in battery deployments for the grid, with the rapid upward trajectory likely to continue or accelerate. Energy Trend has forecast that up to 53 gigawatts, 128.6 gigawatt hours of large-scale BESS installs will occur this year, with China accounting for just under half of that, while Bloomberg has predicted 650 gigawatts and nearly 1.9 terawatt hours of cumulative installs by the end of 2030. And with governments around the world waking up to recognize that they can't have electricity systems based on renewable energy and not fossil fuels without energy storage, it seems highly likely that in any scenario, the role of batteries across electricity networks and in buildings will continue to grow and become ever more central to planning as net zero target dates get closer and closer. Within that context, it's vital that the world invests in batteries. So just today at Energy Storage News, we covered Bloomberg Neff's 2024 edition of its annual Energy Transition Investment Report. While finding that investment into energy storage in 2023 totaled $36 billion worldwide, leaping 76% from 2022 levels, and $135 billion was invested in total in the clean energy supply chain last year. Bloomberg Neff also said that the rate of investment into energy storage, battery manufacturing, and battery metals needs to rapidly accelerate for the world to align with the net zero pledges of the 2015 Paris Accord. And of course, with an industry already rapidly growing and primed for the big time, making sure the systems and components being used are designed, assembled, and able to be operated safely, effectively, and profitably becomes absolutely essential. So joining us today are George Touloupas, who is Senior Director for Technology and Quality at Clean Energy Associates. George leads CEA's technology, quality, and intelligence teams across solar PV, energy storage, and hydrogen. And also Qi Zhang, who is Senior Engineer for Energy Storage and Green Hydrogen at CEA. Qi has been with Clean Energy Associates for more than 5 years and has a background that includes battery system design engineering. So today, this will be a presentation-led webinar, followed by an audience Q&A, and you'll have the chance to put your questions to our experts. So please put your questions for George and Qi into the questions tab on the right-hand side of your screen, and you can put the questions in throughout the session. We'll try and answer as many of those questions as possible, but obviously in the limited time we have, that's not going to be all of them. But Clean Energy Associates representatives will be happy to reach out to you and reply to any that we don't have time to cover in this session. Finally, today's webinar will be recorded and made available to registrants on demand at Energy Storage News. And with that, and without further ado, it's my great pleasure to hand over to our first speaker. Over to you, George.
Thank you, Andy. Thank you for the very good introduction and setting the scene. So today we're going to be talking about the lessons that we learned, and this was based on more than 30 gigawatt hours of best quality inspections, which is dwarfed to what we expect to have this year. But still, it's a very big number, and we can draw extremely useful conclusions. So first, we're going to be saying a few things about the company and what we have achieved and what our activities are. Then we're going to present our multifaceted approach to ESS safety and performance. Afterwards, we're going to see some really cool quality data from this pretty large track record. And then finally, we're going to present case studies and show pictures and show actually real world things that went wrong while we were doing inspections. So let's first start with a quick company and service overview. So Clean Energy Associates is a technical advisory company. It is under the Intertech umbrella since summer 2022. And we're serving IPPs, developers, buyers, financial institutions, EPCs globally for solar PV, energy storage, and electrolyzer systems. We're making sure that the best systems are acquired and installed for projects to operate without problems and be successful. So we have a very big track record for PV solar, more than 250 gigawatts, and as we said, more than 30 gigawatt hours of energy storage systems, offering a range of services from like early stage procurement, market intelligence, supply chain management, then quality assurance, which is the activities while the systems are in production at the factories, and then on-site, of course, engineering services. We have client engagements in more than 75 countries and who have been to hundreds of factories globally. Now, specific to what we are going to show you today and where this is coming from, these are 4 activities that are termed under the quality assurance umbrella, where we have performed factory audits, inline production monitoring, pre-shipment inspections, and factory acceptance tests in more than 50 factories. These were in total more than 360 inspections, and we collected more than 1,300 findings. So a factory audit is based on several hundred points, checklists. It is done on a specific factory location. It's looking, of course, at the quality system, but also at the process. So it's a production line. It can be done on a battery cell manufacturing facility, battery module manufacturing, battery rack, a container, and even finally the integrator facility where the system is put together, a DC block. So this is a very, it's like a qualification step before one goes into mass production. And during mass production, it is very useful and valuable to do inline production monitoring, which are like frequent visits where similar checks are done, but at a smaller scale, again, running checklists. And all these findings, of course, are recorded and classified according to the severity with respect to risk. Also, these activities produce corrective actions that must be followed by the suppliers so that if there is any problem, it has to be fixed before more product is manufactured. The next step is when the product is ready, when we're talking about cells or modules or racks, so numerous like uniform equipment of similar design, then we can do on a sampling-based pre-shipment inspection. Again, the findings are recorded and classified. Finally, when the system is integrated, we're performing the factory acceptance test. These are visual inspection, performance, functional tests, mechanical tests as well. Again, it can be done on 100% basis, but typically on a sampling basis of the DC blocks of course, containerized for utility scale, but if needed for residential batteries. Only the finished goods are audited, the finished products. And again, the findings are recorded, classified, and corrective actions are suggested, and they must be followed and closed. Otherwise, this product cannot be actually shipped. So this is the final step before shipment. So let's see how this is all tied together with quality and risk management and mitigation. As we said, we have a multi-phased approach, and this is needed because the battery system life cycle is quite complex. So starting at the product design validation, we observe that product design can be obviously reviewed and examined by a third party, but more or less it's a black box. And it does contain some very critical subsystems, for example, the thermal management system. So its effectiveness is really important for the lifetime of the battery energy storage system, its performance, and of course for safety, from a safety standpoint. During the procurement of the battery energy storage system, there are several factors that can derail the procurement process. So the manufacturing capability, so there is a promise of volume, can it be produced on that specific factory location or manufacturing facility? Is this location okay? So does it have the systems in place, the quality systems? Is it nice and tidy? Is it running properly, or there are hiccups or other things that can cause concern? So sometimes a facility can be very new. We're called to go in, and even quality systems are not in place, not fully rolled out. And then, of course, going to mass production. A lot of things can go wrong. It's a very lengthy and multi-level because products are integrated to produce the final DC block. It's a multi-level process. For example, the cell process is very long. There are lots of steps. It's quite vulnerable and very sensitive to even minor deviations from the specifications. And further down, there are very manual processes. So we have a supply chain, if you like, that is ranging from the very high automation, super complex, to rather simple steps, but very manual. So that can create a lot of issues. And during in-field operation, of course, this is where all the problems can manifest, where degradation can go above bounds, above what is expected, and also the capacity and the performance of the system can be below what is expected from it. Again, looking at these 4 steps, of course, modeling and simulation are very, very important, and they are done by in this industry by several companies, by the manufacturers themselves. Products must be certified. They are certified, of course, and we are checking this. At the bottom side, you can see CA services, how they range across the life cycle of the product. Before the contract is signed, there are several quality assurance steps. One of them is the factory audit, and then technology due diligence, or even the technical requirements. FAT checklists can be reviewed and fixed if needed. And then, of course, post-contract, when stuff is being produced, it's being made, as we said before, inline production monitoring, FAT, and even site acceptance test on site. So all these are needed to cut down risk, to restrict risk, to have as little as possible. And a very big concern is thermal runaways. Thermal runaways, the boogeyman of this industry. It's not the only thing that can happen, can go wrong in a battery energy storage system, but it's definitely one of the most prominent. And because we're talking about fires, these events immediately get to the news, right? So it's very difficult to hide. It's impossible, basically. So here we have listed some very famous thermal runaway events, the McMicken fire. At the top box, we list some possible root causes according to what has been published, various reports. And at the blue box below is we have listed several steps that could have been done and would most probably have mitigated the risk at the root. So this is quite busy, so I'm not gonna go over all the items, but if you look at the most landing phase 1 and 2, Chi will later show a case study where some steps that we proposed, functional tests, and some QC over key safety components, would have been critical in stopping these events from happening. So let's look at the data from more than 30 gigawatt hours of inspections. So this is a pie chart of everything we have found at the 3 different levels. So the top level is the system. The next level down is the module. And then we're going to the battery cell. So at the system level, we observe that this amounts to around 50% of all the findings. So it's quite a big percentage. Although you can say that, it's a system. It's not a very big, long production line or a very big factory with complicated processes. However, these processes, the integration processes, are very manual. And sometimes we see this integration happening without following very stringent quality control procedures. Also, all the subsystems, subcomponents that are getting integrated have an opportunity to manifest some issue. So everything kind of concentrates at the system integration stage. And that's why we see so many findings. And then at the module integration level, where cells are being put together into modules, the problems are mainly due to the lack of automation. We're going to take a deeper dive in all these 3 areas later on. And of course, at the cell level, it's all about the very complex and lengthy production process. So looking at the system, so at the DC block, if you like, this is an occurrence chart. So what we see here is the frequency of appearance of problems. Now look at the fire suppression system, 26%. That means 1 out of 4 energy storage system units that were inspected had problems with the fire suppression system, which is a shockingly high occurrence rate, frequency. And the next one is the appearance at 23%. And this can be visual, can be scratches, but of course some of these have corrosion risk. So in general, it's a minor. These are minor findings. We're going to see more about this later. And the third one is the thermal management system, which is another big cause of concern. So let's have a look. The pie chart shows the distribution of findings, so it's not an occurrence. It's not related to occurrence, but it's the share of each category of finding in the total finding. One can see that the enclosure is about 1/3 of what we found. And this is mainly due to appearance defects, marking mistakes, nameplates being wrong, like openings in the wrong place or they shouldn't be at all, rigidity issues. For example, lifting provision test, you have to lift the container because that's what's going to happen on site. And then if you put it down and the doors don't open, this is a problem, right? Also, sometimes poor wiring, cable arrangement. This can be potentially a very big risk, either for power or communication cables. Grounding can be problematic. Also, water ingress issues. So, take a water hose, throw water, and it goes in. It shouldn't happen, right? Sometimes it happens because it's a container. Maybe the doors don't seal properly, or there could be some openings where they shouldn't be. The next broader category is the balance of system. Here we have observed liquid coolant leakage. We're gonna see a lot more details about that, but this is definitely super concerning because you need the liquid for the coolant, and second, the liquid next to electrical equipment is a really bad thing. Also, sensors and several mechanisms and alarms are not always installed perfectly, and they might not be working as expected. Even conductors are not insulated properly. So again, live conductor is a very concerning finding. The third area is the performance test. Here we have very few findings relatively to the other ones. And they're related to capacity and relative efficiency, aberrating from what has been agreed. But in general, most of the findings are in the enclosure and the balance of system. On the bottom right, you can see the classification according to the severity of the findings, ranging from critical to major and minor. Of course, the performance test, whenever there's a finding there, it's mostly critical or major. But for the enclosure, it's mostly minor. Now, moving a level down, let's go inside the racks and check the modules, right? So the module is made into a factory where the cells are integrated, are assembled together and soldered, welded to the cable system. So this is a very important subunit. Also has the BMS, the battery management system, integrated. Now, this is again an occurrence chart. What do we see here? That 50% of the inspections we had interconnection welding issues. This is very concerning and alarming because you really don't want to have soldering bond or welding bond failures there. That can cause an arc and, of course, system failure or even a thermal event. The next one down is cell sorting installation. So the cells maybe were positioned the other way around, or the power classes were not, the capacity class were not matching. And why is this happening? Because these module assembly workshops are not very automated. They're pretty manual. I mean, these results are spanning a few years, right? So things are changing gradually. We see that these brand new factories, module assembly factories, cell assembly to module factories, have a much higher degree of automation. So things are bound to improve, but the picture of as of today is this one. So looking at the top findings, cell sorting is the majority, where there was lack of error-proof measures with respect to the assembly and with the right orientation. Then interconnection welding, where the positions were wrong, or the welding strength test equipment was not calibrated, so they weren't really checking for the welding strength. Or there could be residues, welding slags, which is, of course, very concerning because this can cause shorts. And then the enclosure, like wrong barcodes, poorly executed cleanliness and tightness of the workshop. Finally, end-of-life test. This is fails. Right? It's really bad. It's a major finding 100% of the time, but it's a very small percentage of the total findings, because if this happens, there is something really bad, typically wiring insulation, something's touching where it shouldn't inside the module. Finally, let's go up to the cell level. This is an occurrence chart of what we have found by inspecting cell factories, battery cell factories. These are a lot of steps, as you can see. These are production steps, basically. Top of the problems is at the mixing. Then slitting and winding is the next one down, but it's more or less even spread. Perhaps the mixing stage is an exception. It's a bit higher. Now, what goes wrong, right? Looking at the electro manufacturing, where the mixing step belongs, we list some things that go wrong here, like the calibration of the viscosity meter, expiration control of the active material was missing. At the coating stage, again, it has to do quality control, not measured properly, thickness, moisture content, and the calendaring stage. This is always, could be sometimes visible or measured by instruments, so we have seen deformed electrode sheets. And this is very critical because these things can lead to a very large quantity of cells being out of specs or failing later on, or even having a potential for thermal runaway. At the next group of production steps, we're looking at the cell assembly, where the electrode is inserted into the can. So slitting, the burr size control. This is important because if it is out of specs, there is a potential of shorting. Also, the alignment of the electrodes is very important. Again, potential of shorting. And the welding, again. Welding is very important because that keeps the electrical path as it should be, and of course, the can itself shouldn't be leaking. And at the last self-finishing group of process steps, again, we're seeing welding issues, electrolyte filling issues that are related to leakage or out of spec or not well controlled environmental conditions. And with that, I will pass the mic to my colleague, Zhijiang, to walk you over certain case studies where you will see all these things in practice.
Thank you, George. So up to this point, we talked about what things can go wrong through different phases of a project lifecycle. We talk about the multifaceted approach to address these challenges, and especially the important role that quality assurance can play in finding these problems and mitigating the risks before, during, and after the production processes. And through the quality stats we showed you earlier, we had an idea about where the findings, the problems are distributed, and especially the fact that fire suppression system and the thermal management system, the TMS, being the two of the most problematic components on the system level. To add color to some of these problems we talked about earlier, here we are showing you 3 case studies. The first two, they are related to fire suppression and liquid cooling. These has to do with the inconsistency in the manufacturing processes. And the last case study, the third one, we will be talking about the gaps in suppliers' routine FAT protocol. That has more to do with the inconsistency in suppliers' routine practices in their quality control in terms of FAT. So let's get right into the case studies. First of all, we have fire suppression system. And here we are highlighting 6 problems we found on the fire suppression system from our FAT surveys that pertains to a total project volume of 75 megawatt hours that we are doing for multiple clients. And these problems are found at tier 1 integrators located in China. So let's take a look at these problems, right? We have non-responding solenoid actuator that's responsible for releasing the fire extinguishing agent. We have a fire alarm sign that fails to light up. We also see, the ventilation fan spinning backwards due to a miswiring problem. So this problem like this can be really dangerous. Instead of putting the concentrated hydrocarbon gases out of the container, we are essentially sucking the oxygen in to the container. So that's create a perfect stage for explosion. We also see malfunctioning emergency abort button. We also see the non-responsive sensors, the heat, temperature sensors, smoke sensors due to miswiring, and lack of proper piping protection, like you see here with the missing rubber sleeve that can cause potential piping damage. So the root cause with most of these problems can be traced back either to internal component failure, which is the case for number 1 and number 2 findings listed here, where we find a faulty diode within the actuator. And we also find some internal component failure in the fire alarm sign. Or the rest of the problems, they are more or less has to do with the miswiring or misoperation from the manufacturer. And the associated risk usually with any type of fire suppression system failure has to do with the system's deficiency in detecting and stopping thermal runaway events at early stage. I think it's worth mentioning that number 4 finding here related to a failure in emergency abort function, and number 6, potential piping damage. These are 2 of the contributing factors to the Moss Landing fire that happens years ago. This again shows you how important quality assurance can be in picking up the problems at the factory to avoid these tragedies from happening. And when suppliers, their order starts to pile up and they are really under time pressure to deliver, these quality problems can really come up. Moving on to the next case study, we have a case study here on the liquid cooling system failure. So the liquid cooling system really become necessary with increasing adoption of larger prismatic LFP cells. We're talking about 300 amp hour level above cells. So liquid cooling is definitely a more efficient way of cooling compared with the air cooling systems. However, this comes with increasing system complexity. Essentially, with the liquid cooling system, we are introducing an additional coolant circulation loop, and all the instrumentations, the equipment goes into it. And this, of course, introduces additional hazards, including coolant leakage. So here we are highlighting 4 problems, 4 issues that caused either leakage or caused the failure in the circulation system. Looking at the picture here, we have a leakage issue from the deformed flanges, from loose pipe connections, from defective valves, and we also have a burned moss tube on the motherboard of the compressor, which is an essential part of the circulation equipment. So the liquid cooling system failure often, any sort of leakage can develop themselves into internal short circuiting on the DC bus within the container. And that of course can initiate the arcing event and eventually leading to thermal runaway event. And the component failure in the coolant circulation system usually can result in extended period of system downtime. Usually, a properly working TMS, thermal management system, is a prerequisite of running the batteries to charge and discharge. So, so far we introduced you 2 case studies. That's on the fire suppression system, liquid cooling system. This has more to do with inconsistencies in the manufacturing processes. So the third case study we're going to show you has more to do with inconsistencies in suppliers' routine FAT protocol. That's reflected in the 3 highlighted areas. That's electrical safety, gaps in functional safety, and the system performance. So in terms of the gaps in the electrical safety, we have seen deficiencies in ground impedance test. That's where the ground impedance is not tested at all risk-prone areas. We also see deficiencies in dielectric voltage withstand test. So, for example, the lead current is not measured at all major circuits. In terms of the functional safety, we have seen insufficient test protocols on BMS. This has to do with the testing for the protective functions on the BMS, things like over, under, voltage, current, temperature, right? These are not being tested fully at factory. We also see insufficient testing protocols for the fire suppression system. So that's really where you see not all levels of fire alarms and associated safety protocols are being tested. Last but not least, we have the gaps in the system performance test. That's where we see stuff like loosened pass-fail criteria on the capacity or the round-trip efficiency test. So looking at these gaps, right, we really think about how to close these gaps. That's really, we have the motivation to develop our Golden FAT service. So Golden FAT service basically is what we offered at the early stage of the procurement, basically at the contract stage, to help our clients or the buyers to identify and close these gaps in suppliers' routine FAT protocols. So what makes this Golden FAT golden is actually all the work goes behind it. I know we are applying the lessons learned from our long track record of the QA activities, and we have also seen some of the better practices from the top tier manufacturers. So if you are a football fan, precisely American football fan, you can have a good quarterback and you can have an elite quarterback. So really the good quarterbacks, they execute based on what the offensive coordinator told him to do, right? But what really separates the elite from the good is actually their ability to read formation on the other side and to call the plays on the go. So you can consider this Golden FAT as your elite quarterback. And we're even taking a similar approach. The elite, what makes them an elite is that they spend a lot of time behind the scene watching the tapes. So the tape watching process for Golden FAT is actually a desktop review process. That's where we really go through suppliers' routine FAT protocol to identify the gaps. And this is followed by a negotiation phase. That's where we really work with the suppliers to close these gaps. So with this, this concludes all my 3 case studies. And I'm going to now pass the football to George. I see him wide open in the end zone. So he's going to show you some key takeaways from this.
All right, thank you, Chi. I didn't understand a word of what you said because I know football is not the American football, but that's fine. Well, that was a good metaphor. So key takeaways, right? So first of all, there are no perfect factories because the occurrence rate is quite high. We find stuff everywhere, and some of it's quite concerning. So more than 50 factories, more than 360 inspections, 1,300 findings in total. That's quite a lot. Second key takeaway, quality assurance, all these activities that we are doing, is the most efficient means to mitigate risks during mass production, not after. So it's a lot easier and more economical to rectify things that have been implemented in the wrong way or problems at the factory, at the integration facility, before shipment, before full production, and it's all done in steps. So qualification in the factory, then we start production, or even before that, we do the technical requirement review, and then the factory acceptance test. So it has to be done at the pre-contract stage, during production, and not afterwards. Because if you say, okay, I'm buying from a tier one, it should be fine, I have a warranty, etc. Warranties are fine, but you really don't want to have things going on site. Also, it's quite obvious from what we've shown you that the system integration is the most risk-prone process because it's labor-intensive, the degree of automation is low, the quality protocols are not really standardized, or there are big differences. Some are better than others, etc. And in general, there's difficulty in putting all these very different systems together and make sure that they work properly. And the last one is that we have found that there are gaps in the FAT practices. So although there is there's quite a standard practice of having the FAT checklist reviewed by the buyer's engineering teams and then going ahead, putting the contract and executing. In the last few months, having done several of these reviews, we did find a lot of gaps that we were happy to negotiate with suppliers and close them. And we believe that it was quite valuable because we have closed the door to more risk coming into these projects. So, and in general, I think the experience for the suppliers was quite positive because it was easy to implement, so no additional significant cost, but they just forgot to put it in place. So with that, we thank you so much for your attention, and we're very happy to take questions, of which you have a lot.
We do. We have a lot of questions, a lot of really good questions. So yeah, George and Chi, thank you so much for your presentations. And I think, as I said at the beginning, I think even people that are really well versed in this industry will have found some of those things quite eye-opening, and to hear about to hear about some of the problems, I guess, is a little bit worrying, but it's also really good to know that there are kind of processes for improving that whole dynamic, really, I guess. So yeah, anyway, that's enough from me. That's not, people aren't here to listen to me talk, obviously, are they? They are here to hear you and Chi talk, George. So we've got some questions here from the audience. And as mentioned, we're not going to be able to get through all of these, and some of them are a little bit on the technical side and a bit too detailed to discuss within this forum. So please bear all of that in mind. CEA will get to you offline and follow up on your questions. So, and as the whatever depth of technical discussion you desire, I'm sure CEA will be more than happy to indulge. So yeah, so Roman from the audience, hi Roman, and thank you very much for your question. Says, hello George, how does CEA rate manufacturers' quality assurance and quality control programs? Can manufacturers be trusted, or are third-party quality assurance services the must? What are the current trends on the market? That's a great question. Thank you, Roman, for this. It's a simple but still great question. The answer is no, and that was one of the key takeaways. There is no perfect manufacturer or perfect factory or perfect condition. It's just too complicated. And it's not just one manufacturer doing everything in
robotic style factory. This doesn't exist, it's fiction. So definitely bringing a third party in, a very experienced third party in like CA is extremely valuable. And we do see ups and downs, so there's no obvious trend for things getting like ironed out and problems disappearing. Although I did mention before that we expect that the module lines will get very high degree of automation, that a lot of these welding issues will go away or at least reduced. But the need to do quality assurance is still there. So you cannot really trust even a fully automated process, because a wrong setting can churn out a very large amount of bad product. So the due diligence and the third-party oversight is fundamental.
Excellent. Thank you very much. And Gemma, thanks for your question, Gemma, asks, generally, when you uncover major or critical failings during inspections, how do you engage with the OEM to resolve this? In the case where you're taking a sample approach, how do serial failures get addressed across the rest of the batch?
Another great question. So definitely collaborate with the supplier, the manufacturer, and this is a very transparent process. So the buyers are being informed whenever we found something. They're immediately alerted, and we're taking the steps to solve this. Now, you mentioned serial. Yeah, if there is a high degree of certainty that a lot of the same all the same products will have the same issue, clearly in that case something has to be done, so the product cannot be shipped. So there's no other way around it, basically. Unless it is something that can be fixed on all products. Again, with our supervision, we have made sure that the issue has been fixed and the product is ready for shipment.
Piggyback on what George just mentioned, whenever there's a critical problem that occurs in the factory, we also, our engineers, we work with the manufacturers on the root cause analysis, and we help them. We give suggestions and we work with them to figure out the root cause, to carry out the corrective actions. Right? That's also part of the quality assurance activity we're conducting.
Sure. I mean, I guess at the end of the day, these are all companies that have engaged with Clean Energy Associates because they want to have, product that is obviously fit for purpose and everything. So I guess that clearly that, in terms of giving them recommendations for what needs to be remedied, I guess it's very much in their interest to work with you closely on that, really, I suppose.
Yeah, essentially it is, but they don't always appreciate that.
Okay.
But as the relationships mature and the industry matures, we see a much less pushback than we have been seeing a few years ago. So it's becoming a standard approach, and everybody understands that, okay, for a project to be bankable, there must be oversight. A certain series of due diligence activities must happen, otherwise, this is not working.
Yeah, absolutely. Okay, I'm going to change the subject a little bit here with this next question, because, maybe for no other reason than it was one of the most popular questions from the audience, so a little bit of a jump, but Ruthie asked, with all of the pushback in communities where battery storage projects utilizing lithium-ion technology are proposed, do you see the industry moving away from lithium-ion battery technology? But I also want to add in Catherine's question, which is, do you conduct quality assurance on any types of batteries for energy storage systems other than lithium-ion? So I don't know if this is a little bit of a hypothetical question, a bit of a
it's fantastic question.
Sure. Okay.
Yeah. So the answer to Catherine, no, and it's because there's nothing else. It's not that we choose to avoid anything else than lithium ion, is nobody's buying anything else than lithium ion. This is the truth today. Flow batteries have been around for a much longer time than lithium ion batteries, right? And actually, my colleague Chi has worked in the flow battery sector, has a lot of experience. He has experienced this difficulty of anything else gaining traction. Now, what is discussed in general is that if we need a lot of hours of storage, then maybe flow batteries or other technologies become competitive. But as we are today, there is nothing else than lithium ion. Now, the pushback, okay. I'm not really familiar to what is referred to here. It's probably certain communities, not all communities. So it depends. And because of fires, because batteries are not toxic, but if they catch fire, then it's a different case, right? So unfortunately, there is no alternative. But batteries are improving. So it's a much different industry now than it was a few years ago. A lot of things have improved, 9548 testing and so on. So we're confident, optimistic that the fires are a percentage, right? Because as we have gigawatt hours, terawatt hours of installation, there's going to be some fires, but that's no, if it's a very, very small amount. We're optimistic that the industry will react and put some order to their house.
Sure. Thanks very much, George. I mean, sorry, go on, Chi.
Yes, and I just want to add that in terms of if you compare lithium ion to these alternative technologies, right? If we are looking at supply chain readiness, technology readiness, and you add scale on top of that, that has to do with the cost of the system, the LCOS, levelized cost of the storage, right? Lithium ion currently is a clear winner. I think the big question for the other technologies to become more relevant is they need to be more bankable, and this bankability needs to be supported by regulations, like some innovative renovations. I see the UK is coming up with a type of a floor and a roof type of pricing guarantees that can give more clarity for the offtakes. So to make for this flow battery or long duration battery alternative technologies to make sense, right? Things needs to come together for some of the newer technologies.
Yeah, definitely. I mean, really interesting to see that in the UK's proposed policy on long duration energy storage strategy, they actually excluded lithium ion, I think, at this stage from being eligible for funding because it is to be a high level. But on the other hand, where we've seen solicitations for 8-hour duration storage resources, particularly in Australia and California, two examples that are very prominent, they've been won largely by lithium ion batteries. So yeah, there's definitely a long conversation to be had on that, really, I guess. So yeah, thanks very much.
We can have another webinar just on that.
Say again, sorry?
We can have one more webinar just on that.
Absolutely. Okay, terrific. So coming back on to the lithium batteries, or maybe this is something that might apply to some other types of batteries as well, but Philip Richard asked about, and the reason why I'm asking is this is someone else also asked, Adam Schultz also asked this, how do you check for interconnection welding being done properly, and do you need to observe a large sample of module connections?
Would you like to take this?
Yeah, I'll take this one. So for interconnection welding, typically the method for inspecting the core is to inspect the cross section of the weldment to see if there are any cracks or defects in the welding quality. So it's a type of a destructive test to see what the quality of the welding. And the manufacturers, they do this on a sampling basis for every shift. That's the current practices.
Okay, terrific. And there's a question here from Wakas. Thanks for your question, Wakas, who's asking about under the section of system level findings and then enclosure findings, how often are you finding issues that are related to design versus manufacturing or workmanship? So maybe not just in terms of raw numbers, but like, in terms of the dynamic, really, I suppose, there.
So the question is whether there's a finding that is related to defective design as opposed to the design manufactured improperly.
Yeah.
We don't have this breakdown here, but Chi, do you think we could answer it, or we can come back later?
We can come back later, but things on top of my head is that we have fewer design-related issues, definitely a lot fewer than the workmanship related. Is because, right, at the stage of FAT, the product's already going through so much design validation, and even before the FAT, they have usually what Integrator does is the product validation test. So there are serious tests to make sure the design is on point. At the point of we're doing the FAT, usually all the design issues have been already resolved. So we don't actually find much design-related problems, right?
But sometimes we do. So I think there was a case where a BMS cable was improperly, the path of the cable was improperly designed, and there was a thermal event during our FAT. But it's quite rare.
Okay, so the proportion would be more on the manufacturer rather than design.
So this was like a root cause analysis, and then there was a design change. But yeah, it's very rare because products go through a very long qualification, evaluation, validation process before they go into mass production. There's a big risk if this is not done properly.
Okay, and a question here from Dominic. Thank you for your question, Dominic. And we had a few questions from the audience around testing and certifications, particularly, I think there was definitely more than one question on UL 9540A, and this is one of them, I guess. But Dominic was asking, how far away are type certifications for cell, module, and unit levels that will take over from UL 9540A tests within the market? So, I mean, just from my very simplistic view of the industry, I guess I'm hearing from quite a few people that there are limitations with UL 9540A, and we've done whole webinars on that subject itself. So yeah, maybe we don't need to spend too long on it, but what do you guys see as the future in terms of those types of essential tests, I guess?
Personally, I think the UL 9540A is going to remain as the priority when it comes to the thermal runaway events, because from what I see, right, is the standard, is a code that's being more frequently updated based on the lessons learned from the industry. And if you look at the new version of UL 9540A, it starts to incorporate requirements on the liquid cooling system. They need to undergo the pressure test, and it starts to incorporating the AC blocks, right, with the AC energy storage system with embedded PCS. So it's a more frequently updated code, and I see in short term UL 9540A is going to be the code that's going to be valued by HJs when it comes to the seeding of the actual projects.
Yeah, absolutely. And I think some of that community pushback that Ruthie was referring to earlier on, that's something we do see a little bit of evidence of. We've seen some, particularly counties in New York State, passing kind of moratoriums on battery development. One in, I think, California quite recently as well. But yeah, obviously, industry engaging with all of these concerns that people have is is absolutely essential, I think. So I think we're more or less coming to an end to our session today, everyone, and it's been really, really, really interesting. I'm sorry, I'm just getting distracted because there are so many good questions coming in, and we just aren't going to be able to get to them. But yeah, I'm sure George, Chi, and the rest of the team at CEA will have a lot of fun, really, I guess, and a lot of interesting engagement with the folks that ask those questions. So I don't know if there's any one final question you want to pick from the list, George and Chi, or if there's a takeaway you want to leave us all with before we go. It's not compulsory, but I figured if you want to have a quick.
I mean, a takeaway is that there is no perfect production line or supply chain or manufacturer or tier one, and all these terms mean something, but they don't cover all the risk. So definitely doing due diligence in the factories before procuring even, and then in the factories is a must for buyers. The industry has matured a lot, but it's not there yet. I think that's quite obvious.
And if you have a choice between a good quarterback and an elite quarterback, you always go with the elite.
Just caught that one. Thank you very much. Okay, folks, I just want to say thanks so much to all of you that registered and joined us today. As mentioned, you can watch the session again on demand in the coming days on the Energy-Storage.news website. And finally, from my point of view, I just want to thank you all for being part of this incredible and vibrant industry. And it's got a really important role to play, and I don't need to be telling you all that. I'm sure you already know, but sometimes it's good to reinforce these positive messages, I think. So I want to thank, with all my heart, I want to thank Clean Energy Associates for taking part with us today. Thank you so much, George. Thank you so much, Chi.
Thank you.
Thank you. Thanks, everybody.
And and ultimately, thank you so much to the audience. We'll catch you all very soon. Thanks and goodbye.